welcome to this week's topic, hash tables. This is something very fundamental to understand as we move into more complicated algorithms. And there's going to be times where we just have problems that I want you to explore, and they're going to become a lot easier with hash table implementations. Ultimately, though, they're an abstract data type. So if you have taken a data structures class, or you have some experience with hash tables, this is still going to be interesting because we're going to talk about how to calculate the keys. But before that, I'm going to give you a basic understanding of what a hash table is. The most naive example that you can have, for example, is, so also to get a fixed lookup time, we're looking at big O of 1. That's a big thing to point out. Like we want it to be the same if you're looking for one index versus the other in a predictable time. So let's just say that, for example, we're going to map 1, 2, 3, 4. These are integer keys. Very simple. And maybe we're mapping people's names to it. So let's just say Adam, Dan, Mike, and then maybe Andrew. And now all of a sudden we want to add another person to it. So maybe we also want to add Autumn here, maybe Cassidy here, for example. Notice that in this example, we actually allow multiple values to be entered into the hash map, the hash table. So that's a variation of this. So there's two different options. There's one where the key maps only to one value, so that when you change that value, it will overwrite it. The other is that you look up the key and then there is a subset of data below it. And first off, I want you to think for a second, when would this be bad, right? So this would be bad specifically if we're implementing this with arrays, where the keys, for example, are maybe an array. So this would be like 1, this would be 2, this would be 3, this would be 4. But ultimately what this is pointing to is maybe this is another array, for example, a list of arrays with just Adam in it. And then this one would be Dan and Autumn. Okay, so you've got an array that's pointing to a list or another array. With this implementation, it's rather simple. Your lookup time is not necessarily constant unless you do something that's very inefficient here, which is make it so that we index into this array at different values. So what I mean by that is, so let's say that we want to make it efficient first. So we're going to actually have an index 0 here, and we have all the possible values allocated. So let's say that all of a sudden we add a 10 billion index, a key that we want to look up. So that now we need to create all the numbers in between here up to 10 billion. So what do we end up with if we're only using these keys and all of a sudden this key? We get an enormous amount of memory that is just not useful. We've got allocated memory that isn't being used. So what are some better ways to do that? We're going to talk about that, but first we're going to nail this down into what operations we actually want to do. We want 3 operations. We want to be able to insert a value in a key. We want to be able to delete. And this would be a, depending on how it works, but typically you remove just the item. Search, you can do the key. So you basically would say, return me the things that are in with key 3. So that's what we're going to be trying to implement. And the right way to do this is to use other data structures to actually implement it. Arrays are not going to be ideal. But we also run into another problem. What if our key becomes our name? So let's talk about a good example here. An example would be a phone book. A phone book may have a key associated to a person's last name and then first name. So we would have both of those. That'd be like Larson Adam, and this would be my number. And then we'd have another one, and another one, and another one. How in the world do we take our name and make it into something that we can look up in fixed time? So that's problem one, and we're going to talk through some solutions for that. Problem two is we still know that we need our keys to be something that we can, probably a simple way to put that is we need that to be something that's easily represented in memory. And if you think about the way that memory works in programming languages, for example, basically everything boils down to bytes. So, you know, the number 1532 is equal to some bytes. And then a string that is equal to, you know, something here. So this would be like Larson Adam is equal to some bytes. And let's imagine this is like a byte structure. So let's just pretend that this is not going to be correct, but let's just say this is all in hex. So something along those lines, and maybe there's more here. So we know that we can take a string and convert it into something that can be represented as a number, just based on the standpoint of we can take a subset of a string and grab a section of that data out if we even need to, depending on how that string is actually created. So, is it fair for us to just directly map a string to an integer and create it the way that we're talking about in the array? And the answer to that is no, because we're going to end up with this massive amount of memory that's allocated that's not important. So this is a large number, for example. This does not currently map to that, but it could, right? Something similar to that. Some amount of data would map to that. And if we were doing it as an array, that would cause us to have to allocate an enormous amount of memory and have a lot of wasted space. So well, first thing that we need to solve is some ways to actually map anything to some sort of key value. So there are ways to do that, and typically you're going to hear things in your career that are called like hashing functions, hashing algorithms. And typically, this is going to be a function or a formula that takes in some value. So let's just say in this case it's a string. So it takes in some value, and it's going to return a hash value. Okay? An important thing to note is that if you were to pass in Larson Adam multiple times, you need to be able to consistently get that hash value. And for those of you that are very interested in like cryptocurrency, they also have this thing called, let me make sure I spell this right, cryptographic hashing functions. And so if you're interested in that, cryptographic graphing function, or I mean hashing. Hashing. Those are quite fascinating as well, because they really work on making sure that you can hash one direction, but it's very hard to come back the other direction at a very high level understanding of that. So now that we have this hashing function, why is any of this even important? So let's take a look and think about the reasons why hash tables are used today. So if you think about compilers, for those of you that actually have worked with compiled languages, that being those of like Java or C++ or C#, a lot of the code that you're doing is getting simplified down and used. Hash tables and hash maps are used very commonly to map where certain things are happening. So compilers use them quite a bit, so it's good there. Databases also. Could you imagine like storing a, for example, like a phone book or any sort of large massive data set without having some way to quickly look up based on name or whatever your key happens to be? And the other thing is, in hardware, they're surprisingly useful when you're dealing with like a bunch of a complicated network system, and you need compilers and switches, or not compilers, routers and switches. So you're sending a network message in, that's getting routed to a certain area. Based on the identifier for that end client, it knows how to route that through the proper path to get there. So it's pretty cool. So that's why we know that we've got a hash function here that returns a hash value. We know basically that that hash value is going to be used for a key to store whatever that value is. So for in this example, this would be my phone number. We would be hashing my name, and we would then be able to, if we were to ever look for that, we'd be able to look up that specific phone number based on my name, because that hash value would be done the same way every time. So what goal do we actually have? Because this hash value still has the same problem that we've talked about the entire time. Our ultimate goal is to limit the number of keys to something that is as close to the number of data items or values there are. For example, if we have 1,000 names in a list, maybe it's a company directory, we would like our hash table to be as close to 1,000 items as possible. And if we use that array approach, we end up with a range from whatever key value that is, if we want them fast indexed. So another way to do that is you can use something like a list. So let's say, for example, let's just run through an example of this. We take and get rid of all this stuff up here. We'll remember our goal, and we're going to try to get as close as we can to that with the knowledge that we have today. So a list, on one hand, is something that looks something like this, right? So we have a node, and it potentially has a pointer to another node, which actually could go further, right? In our scenario here, we actually can have a pointer back, and we can have a pointer back here, okay? So basically we can travel down, or we can travel back up. And in this node, the node could actually be pointing to another list of items, and this one could be singly linked because we don't really need to be able to track back. And this would be holding the value. So this would be value 1, value 2, or value 3. In a case that we want to store multiple values. So, for example, in a phone book, you would have one phone number typically, although more realistically nowadays, that may be like if it was a company directory and we wanted to store all my possible phone numbers in there, it could be my work phone, it could be my cell phone, it could be my backup phone. I do not have a home phone, but it could be in that scenario. Where this would actually be my name. So, how do you actually navigate through this? You would start at your head node, and you would navigate through when you do your hashing algorithm until you found the key. And where it says Larson Atom, that would actually be your key. that is hashed in that example. So what the problem with this approach is that as your list grows, you need a faster way to get there. Because remember, our goal was to be able to look up very fast. In this scenario right now, we end up with a big O of n lookup time. There are ways to improve that. Specifically, if you have the data that you need to, you can do a binary lookup. So what I mean by that is you can actually split your list into let's just imagine that we have 4 items here. Let's do it with 5 because it's easier to show. So if we know that this list is sorted, one of the things that we can actually do is we can potentially grab the node if we have a start node here and we have an end node here, right there. If you can find the center point, and the way to do the center point with the list is a little bit more complicated, but typically what you do is you just move both of them forward until you find the center point. The problem is in that scenario, we don't have a direct lookup. So if we were to find that, if we had the center point in this linked list scenario, and we had bidirectional, we could actually take and we look to see, okay, is the value of this greater than or less than? Do we need to go to the next center point, or do we need to go to the next center point? It works really well if we have access to that center point. To get access to that center point, like I said, we would have to start at the beginning and end, and we'd have to walk up each way till we find the node that both of them are at, and we know that we've traveled an equal distance, or we're at least off by 1, right? So I mean, if it's an even number, for example, the 4, we're just going to be off center by 1. So we know that binary search doesn't work that great there. So what are some other options that we can use to create an efficient hash table? And we start looking into trees. Trees are really the answer to how you actually create a great hash table. Because if you end up with a tree, let's get rid of all this. So that's linked list is 1, array was 1. So just to keep that clear, we had option 1 was an array, huge memory hog. Linked list way better on the memory side, but less efficient. So what have we done? We've sacrificed efficiency to save memory, because you only need to add a node when that item is added. So you don't allocate memory unless you need it. So we end up with an exact mapping. But let's imagine that we have a tree of sorted keys. So we end up with something similar to a binary tree. So we get doot doot. And each one of these nodes point to, so these are the keys, and each one of these nodes ends up pointing to, this could be an array, because depending on what the items are, it could be a single value, or it could be a list. Doesn't really matter for what you're pointing to, how you're storing the data. Typically you want this to be as small amount of data as possible. So now let's say that we're now looking for a value of 10. We come in here, and we know, okay, we're going to go less than, all right, we need to go greater than, this is the value that we need, and we end up with our return. So this ends up in a logarithmic lookup time. Very efficient, and the most ideal method with the knowledge that you have today for actually creating a hash table. So if you understand hash tables, they can be created very simply with more simple data structures such as linked list and arrays. But when you really want to start getting them to be efficient, you're going to want to look for a tree implementation. So we get the same thing. We get the number of keys are only created as needed. If we need to do an insertion, we add a new node and manipulate the tree correctly. So the one other thing is insertion ends up being a logarithmic time as well too. So we go instead of a constant time, and deletion can also be the same depending on where it actually comes out. Sometimes you can get a better time complexity. Whereas a linked list, you end up with a constant time insertion, plus the sorting. So typically if you're adding it to a already sorted list, you would have potentially a big O of n time to find the location, because you would need to scan through to find the spot. And insertion time at that point would be big O of n plus the constant time of creating it. In this one, you would need to find the spot and do a logarithmic insertion, because finding it is actually logarithmic time. Creating or inserting it is also a constant time, because creating that node and inserting it. So that's 3 of the methods for actually creating a hash table. I would like to dig in a little bit into what the possibilities are for this hashing function. So let's talk about a really bad one. So let's just take, for example, that we have this key of value. So let's just say maybe it ends up being some really large number. So let's say it ends up being like 4223123 4% m. So, and let's just say %m. And the only reason I'm putting this number here is this would be the val. So maybe we have to make that even more clear. Let's just write this like we would actual code. So let's just say the val, the modulus of m. Now what is m in that case? M, and this should actually probably just be assigned to the HR hash rate. So m is some number that you come up with. So an example of this would be like some large number, like 422715998 $259. This is a really bad one, because what ends up happening is you get a lot of clashes. You have 259 potential indexes that you can use. So I mean, that's a good thing, right? You've limited your memory to 259. The bad thing is there is literally the chance of collisions when there shouldn't be collisions. For example, if we're dealing with 1 million names, we don't want names that start with an L and names that start with a Z to collide, just because the remainder, if you don't know the modulus is the remainder, happens to be the same in that scenario. So let's talk about one that maybe could work. So there's a little bit more complicated one. And we're assuming that val has been converted to a number, by the way, even though I passed it in as a string. So let's say that we do something like this. A times k mod 2, actually we're going to do modulus 2w, and then we're going to right shift this w minus r. So this is how complicated some of the even very naive examples of hashing functions are, where your k is your key, and then you end up with a few other constant values that you end up working through to help modify and maybe make the algorithm change. So you could try playing around with changing those values and how they actually turn out. And what ends up happening is, like, usually A is just defined as something that you've specified, and then notice that W also affects the right shift in this. So an example of this would be, like, if we were to draw it like this, for example, and again, this is going to be really hard to show, but let's just assume that width is the number of, by the way, width is the number of bytes that you're looking for, just to make sure I clarify that. So let's just assume that we're looking for width here. Okay. And this just happens to be, I don't know, whatever it is, whatever W you set to. And you want to take this value of A here, and you're going to multiply this by some value of K. Maybe, actually, let's do this. And then your K value ends up maybe being larger, right? So maybe you've got a bunch of you're basically chopping off some of these bytes. And again, my numbers don't line up exactly, but that's really what you're doing in that scenario. So then this returns a much more, I'd say, a much more manageable, so it's a little bit wonky and it can be good with certain data, and you can play around with how much data you want to use and how little data you want to use, and you can play around with a few other settings in here. And then you take the right side here, which is basically the width of the bytes that you actually want to do, and you want to right shift that over, and you don't want, this is basically just to exclude the right side over there. So we would come up with a value that would be our new hash value. That hash value would get turned over. It's a fairly quick mathematical formula, even though the modulus operator can be somewhat inefficient. Right shifting bits is pretty good. Multiplication, which is what this is, multiplication, get rid of that. To the power can actually be somewhat expensive depending on what W is, especially with W being in the 10, but it's still a very predictable, very constant speed hash value calculation. So if we end up getting this to produce a value that we feel comfortable with a decent spread of collisions not happening, we can insert that into that tree and we end up with a really cool hashing algorithm. This, by the way, this one's not great. There are millions and millions of others, which leads me to your assignment. So just remember what a hashing algorithm is supposed to do. So your assignment is actually going to be very fun. So I would like you to explore maybe doing some research, maybe even getting brave and going through the cryptographic algorithms. I don't even necessarily need you to implement it. I would like you to find a solution that you think would work for this. But let's say that for your assignment, we are going to do a hash function. So takes as input. Input is a integer key. I'm trying to keep it simple. From the range of 0 to max int. Depending on the language you're in, I just want you to take massive indexes there. And I want you to write a hash function that you feel comfortable with. So it would look something like this in JavaScript. So we'd have function, hash, and you would have var key. You would do something with this key. So this would be your code, and then return a hash value. So something there. And whatever language you choose. So I want you to take a hash function. I want you to write a hash function that takes an integer key from 0 to max integer. Now I would prefer if you did it with a string, where you actually are taking a string and converting it to an integer. But the complexity in that can be a bit extreme in certain programming languages. So let's just keep it simple and assume that the string value has already been converted to an integer for you. So that's why I'm using this 0 to max integer. So this would go under the assumption that I've given you a large string. That large string has been put into a numeric value that now you're hashing because we've converted that string into a set of numbers. So it needs to return a hash value. Now it needs to be consistent on calculations of the same key. So if you pass in the number 1, for example, it needs to return the same hash value every time. If you pass in the number 10, it should return the same hash value every time. So then I want you to do a half page write-up on your solution. So I want you just to give me your thoughts on your solution. Maybe you have multiple that you tried. Maybe you found one that you worked better than others. I would like you, and this should be something that you do in your career forever, but I would like you to think about edge cases when you're feeding data into this hash function. And I would like to make sure that you handle cases of what happens if I hand you a value that is not in the range of 0 to max integer? What happens if I hand you a value that maybe, I'm trying to think of some other solutions, maybe is null, right? So maybe it isn't even a value at all. What happens if I hand you a negative number? What happens in the situation that you feed in values that are close to each other? So what, do you get a different hash score consistently when you feed in 10, 11, 12, 13, 14, 15? It'd also be cool if you ran maybe a test to determine how many collisions you get on a subset of 1,000 random numbers from a pretty large range. So feel free to do as much research as you want. Feel free to try out algorithms that are online. Feel free to use libraries for the hashing function. Feel free to come up with your own that you think are cool. I just want you to kind of play around with the idea of creating a hash function. And I would like you to give me this in a file that is runnable on my end. So if that is JavaScript, you can give me a single JS file, or even like a JS fiddle or CodePen link that I can play around with. If it's a different language like Java, send me the Java file. C#, send me the project. And the half-page write-up, please include that in there as well. And if you have any questions about it, please reach out. But hopefully doing this in video has better explained this. Alright guys, hopefully this has been fun. Hash tables are something that can't really teach you all the complexity about it in a single lesson. It's really something that you're going to have to jump into and start developing on. And I would say on the flip side of that, if you haven't taken data structures, hopefully they talk about how to actually implement proper hash tables beyond even the scope of what I covered here. Alright, till next time, take care.